everyone, welcome back to Sulekha physics classes. It is the most easiest way to learn all the concept of physics through this class. Today I am going to start one short revision of chapter 13, that is nuclear. In this chapter, many topics are deleted for this year. Only 2 or 3 topics are left. That is, you have to study about composition and size of nucleus, then mass energy relation, mass defect, and last nuclear reaction, that is nuclear fission and fusion. Other topics like radioactivity, alpha beta gamma emission, their properties, radioactivity K law, then binding energy, and then its variation with mass number. All these topics are deleted for this year. So no need to study these topics for examination point of view. Only 2 or 3 topics you have to study. You have to focus on those topics, right? So I already told you about that chapter 11 plus chapter 12 and chapter 13, dual nature of radiation and matter, then atoms, and this one nuclear. All these 3 chapters alone consist of 12 marks. And these chapters are very small, very easy theoretical chapters. It's very easy to score 12 marks from these 3 chapters within 2 or 3 days revision. So you must revise these 3 chapters, right? This chapter is very small and it's very easy also. So let us start quick revision of this chapter nuclei right now. First topic is composition of nucleus. What is first nucleus? Okay, in the last chapter we discussed about Rutherford alpha scattering experiment, and in that experiment Rutherford observed that an atom consists of a central massive positive core, and that core is called nucleus, surrounded by negatively charged electrons. Negatively charged electrons revolve around that positively charged nucleus. So what is nucleus made up of? Okay, after study of radioactivity, it is observed that a nucleus is also consists of subatomic particles, that is protons and neutrons, right? And these protons and neutrons are collectively known as nucleons. It means the nucleus of an atom consists of protons and neutrons, which are known as nucleons. What are protons and neutrons? Who discovered protons and neutrons? Protons are positively charged particle, and it was discovered by Rutherford, you know, right? And these neutrons are neutral particles. It does not have any charge. There is no charge on this neutron particle, right? And it was discovered by J. Chadwick, and you know electrons was discovered by J. Thomson experiment. Okay, so an atom consists of nucleons. In nucleons, protons and neutrons are present, surrounded by negatively charged electrons, right? Now, there are different terms related to the nucleus of an atom. First one is atomic number, then mass number. What is atomic number? It is number of protons present in the nucleus. Inside the nucleus, protons are present. So how many number of protons present in the nucleus? That number of protons is called atomic number, and it is represented by capital letter Z. And the number of protons is always equal to number of neutrons in any atom, so that the total atom becomes stable, right? To maintain the stability of the atom, number of protons, it means positive charge, becomes equal to the number of electrons, that is negatively charged. Okay. Then next is mass number. What is this mass number? It is represented by the capital letter A. It is total number of proton and neutrons present in the nucleus. Inside the nucleus, both protons and neutrons are present. Both are called nucleons. So how many total number of nucleons present in the nucleus of an atom? That is called its mass number. It is represented by capital A. So you can write number of protons P plus neutrons, it is equal to nucleons. And this total nucleons is mass number, represented by A. So let us suppose that number of protons in any atom is what? Atomic number, represented by Z. So number of electrons in any atom is also Z. Number of neutrons in any atom is suppose N. And number of nucleons is number of protons per neutrons, and it is represented by capital letter A, mass number. So number of nucleons is represented by A, and this A is equal to number of protons plus number of Neutrons, protons means atomic number Z. From here, you can easily calculate number of neutrons, that is N equal to A plus Z. It's very simple and easy formula. In 1 or 2 marks question also some numericals based on these formulas. If atomic mass is given, atomic mass means number of protons is given, number of neutrons is given, you have to calculate what is a mass number. Yeah, or mass number is given, number of protons is given, you have to calculate number of neutrons. So you have to use this formula, right? After this one important definition is nuclear mass. It means mass of the nucleus, or you can say atomic mass also, or atomic mass also. An atom consists of protons and neutrons, that is nucleus, surrounded by negatively charged electrons, but the mass of electrons is very small, right now. So whatever is the mass of nucleus is the mass of what? Atoms. So what is this nuclear mass? Inside the nucleus, what is present? Protons and neutrons. So total mass of protons and neutrons present in a nucleus is called nuclear mass, or you can say atomic mass. Mass of the atom also, because inside the atom electrons are present, but mass of electron is very, very small. So whatever is the mass of nucleus is the mass of atom, right? Total mass of protons and neutrons. And any nuclide or nuclear species is represented by XAZ. X is any symbol of any species, any element, carbon, oxygen, nitrogen, anything. Z is what? It's atomic number. A is what? Mass number, right? So if, okay, why I have written this one? No. Suppose for example oxygen. Oxygen, what is the atomic number of oxygen? That is 8. And its mass number is 16. So you can write O816. Example nitrogen. Atomic number of nitrogen is 7 and mass number 14. So it is just representation of any nuclide with atomic number, mass number and its symbol, right? So please take a screenshot of this one. After that we will discuss what is the unit of this nuclear mass, atomic mass, because SI unit of any mass is kg, but the mass of nucleus or this atom is very small. We can't measure it in kilogram. So there is another special unit to measure nuclear mass or atomic mass, that is called atomic mass unit. I will discuss after this one. And also one more thing, the size of nucleus is very, very small as compared to the size of atoms. Right now size of nucleus is in the range of what? Fermi, 10 to the minus 15 meter, and size of atom it is in the range of angstrom, 10 to the power minus 10 meter. The size of nucleus is very small as compared to the size of atom, right? So we will discuss next atomic mass unit. Please take a screenshot of this one first. Now atomic mass unit, as size of atom is very, very small, so is mass is also very small as compared to kg. So there is a different unit to measure atomic mass. So atomic mass is measured in atomic mass unit. In short form you can write AMU, or also you can write U. And what is this atomic mass unit? One atomic mass unit is defined as 1/12th mass of carbon-12 atom. As the mass of carbon-12 atom is very, very small, so that is used to measure one atomic mass unit. So you can write in this way, one atomic mass unit is 1/12th of mass of carbon-12 atom. Now what is mass of carbon-12 atom? You know mass of 1 mole of carbon, or you can say in 1 mole how many atoms? 6.023 into 1023 atoms, and this is equal to 12 gram, right? So mass of one atom is how much? 12 by 6.023 into 10 to the power 23 gram. This is mass of one atom of carbon-12. And what is atomic mass unit? 1/12th into mass of carbon-12 atom. So you can write in this way, 1 AMU equal to 1/12 into what is mass of one carbon atom? 12 by 6.023 into 10 to the power 23, and this becomes equal to 1 AMU equal to 1.66 into 10 to the power minus 27 kg. So 1 AMU is so small, you know 1 kg, and 1 AMU equal to 1 1.66 into 10 to the power minus 27 kg. So the mass of the atom is very small. That's why it is measured in atomic mass unit, right? This atomic mass unit is measured by an instrument called mass spectrometer, and also this is mass of proton and also mass of neutron. Mass of proton is how much? 1.67 into 10 to the power minus 27 kg. Mass of neutron is also 1.67 into 10 to the power minus 27 kg. And mass of electron, you know, 9.1 into 10 to the power minus 31 kg. Mass of electron is also very small as compared to proton and neutron. So total mass of any atom is nothing but mass of proton plus mass of neutron, which is present inside the nucleus. And this is also atomic mass, you can say nuclear mass, because mass of electron is very small. And in one atomic mass unit, 1.66 into 10 to the power minus 27 kg. You must remember this formula. It is very useful when you solve numerical, right? Now after this one, there are different types of atoms, or you can say nuclei, right? First one is isotopes. Isotopes are those atoms having nuclei which have same atomic number but different mass number. Different atoms or their nuclei have same atomic number but mass number is different. Like here, isotopes of hydrogen, atomic number is what? 1 here and 1 here also, but their mass number is different. Here 1 and here 2. Again, isotopes of carbon, atomic number of carbon is what? 6, right now, but their mass number, one have mass number 12 and another have mass number 13. So if atomic number is same, mass number is different, that type of atoms or nuclei are called isotopes. Next one is isobar. Isobar is opposite of this one. Those atoms which have same mass number but different atomic number. Here mass number is same but atomic number is different. So in isotopes, same element is there because atomic number is same, but in isobars, atomic number is different. It means elements are also different atoms are there. So here suppose example, carbon and nitrogen. This carbon has 6, how much? This 6 atomic number, and nitrogen has how much? 7 atomic number. So here atomic number is different but both have mass number 14. These two elements, carbon and nitrogen, are isobar. Again, chlorine and sulfur, both have, chlorine has 17 atomic number and sulfur has 16 atomic number, but their mass number is same, 37. Okay, so you must revise this one. You must learn 1 or 2 example also for isotopes, isobars. Next one is isotone. Here both atomic number and mass number are different, but their number of neutrons are same number of neutrons but different atomic number as well as mass number. You know, number of neutrons is what? Mass number minus atomic number, A minus Z. Suppose here example, boron and carbon. Boron has atomic number 5 and mass number 12. Here carbon has atomic number 6, mass number 13. In both elements, atomic number is also different, mass number is also different. But if you find number of neutrons is what? Mass number minus atomic number. So here number of neutron in case of boron is what? 12 minus 5. It means how much? 7. And in case of carbon, number of neutrons how much? 13 minus 6, it again 7. So both boron and carbon has same number of neutrons but their atomic and mass number are different. This type of atoms or nuclei are called isotones, right? And one more, last one, isomers. Those atoms which have same atomic number is same and mass number is also same but different energy state, right? So you must revise these 4 types of atoms or nuclei. You can write types of atoms or nuclei also. Nuclei is just present inside the atom. First one is isotopes, then isobars, then isotones and isomers, right? So please take a screenshot of this one. After this we will discuss size of nucleus. Now after composition of nucleus, next is size of nucleus. Size of nucleus has been measured with the help of different experiments involving scattering of particles such as electron, proton, neutron. And in all these experiments, it is observed that volume of nucleus is directly proportional to number of nucleons, and number of nucleus is number of protons plus neutrons. It is also called mass number of nucleus, which is represented by A. So experimental observation shows that volume is directly proportional to mass number, and nuclei is of a spherical shape. So volume is what? 4 by 3 pi r cube, where r is radius of nucleus, and this is directly proportional to mass number A. A is mass number, right? Again, from here, these are constants. So r cube is directly proportional to A, and this r is directly proportional to A to the power 1 by 3, or you can say cube root of A. And then you remove this proportionality, you get r equal to r naught A to the power 1 by 3. This represents size of nucleus, and this r is radius of nucleus. It is equal to r naught A to the power 1 by 3, where A is mass number. What is this r naught? R naught is a constant called nuclear unit radius. It is in the range of Fermi, and its value is 1.2 into 10 to the power minus 17 meter. It is called nuclear unit radius. R is radius of nucleus, A is mass number. So size of the nucleus is directly proportional to mass number. Okay. Now after this, nuclear density. Density, you know, mass by volume. Here you have to find density of nucleus. So mass of nucleus, because nucleus consists of nucleons, that is protons plus neutrons. So density of nucleus is mass of nucleons by volume of nucleus. Then mass of nucleons, how you calculate mass of nucleus? At mass number of nucleons is A is mass number. If you multiply it with M, and its value is what? At 1 atomic mass unit. M is 1.67 into 10 to the power minus 27 kg. So mass of nucleons is M into A divided by volume of nucleons. It is 4 by 3 pi r cube. From here, you put the value of R. R is what? R naught A to the power 1 by 3. And then cube root. It becomes MA by 4 by 3 pi R naught cube. And then this cube cancel, only A is left. Again here A cancel, and this density becomes, put this 3 in the numerator, 3m by 4 pi R naught cube. From this expression, it's clear that this nuclear density is independent of radius, mass number. It means nuclear density is independent of mass number, and radius means what? Size of nucleus. It shows that for all the elements, nuclear density is same. It is independent of mass number and size of nucleus. And its value is, if you put the value of M, this one 1.67 into 10 to the power minus 27 kg, R naught is 1.2 into 10 to the power minus 15, you get density, this one equal to 2.30 into 10 to the power 17 kg per meter cube. And here power is 17. It means nuclear density is very, very high, right? And its value is this one. So from these things, it is clear that size of nucleus is directly proportional to mass number, but nuclear density is independent of mass number and size of nucleus. This point is very, very important. It may come in 1 or 2 marks question, that how nuclear density varied with mass number and size of nucleus. It does not depend on mass number and size of nucleus. For all elements, nuclear density is same. Okay. So after this, we will discuss what is nuclear force and then mass defect. Okay. Please take a screenshot of this one. Next is nuclear forces. You know, inside the nucleus, protons and neutrons are present, and there is a strong electrostatic force of repulsion between protons, but still protons and neutrons exist inside the nucleus due to nuclear force, and this nuclear force is very strong force, right? Nuclear force is a strong force of attraction which hold together the nucleus, which hold the protons and neutrons in the tiny nucleus of an atom in spite of strong electrostatic force of repulsion between protons. It means inside the nucleus there is a strong force of repulsion between protons, but still protons and neutrons hold together inside the nucleus due to these nuclear forces. So there are different properties of this nuclear force. It is the very strongest force is nature, right? It is stronger than gravitational force, electrostatic force, right? It is a short range force. Inside the nucleus this force exists, so it is a very short range force. It do not obey inverse square law, and also it is charge independent, and last one, non-central force. So you must remember 2 or 3 properties of this nuclear force, right? After this, next one is mass energy relation. According to Einstein, mass and energy are equivalent. Mass can be converted into energy and energy can be converted into mass. So according to Einstein, mass can be converted into energy by this relation E equal to delta m c square, where c is the speed of light. Its value is 3 into 10 to the power 8 meter per second in vacuum. Okay. Next, the mass of particle in a frame of reference in which particle is at rest. When the particle is at rest, its mass is called rest mass. It is represented by m naught. So, total energy of any particle is sum of kinetic energy plus rest mass energy. Rest mass energy is what? M naught c square. This is rest mass energy. And suppose K is kinetic energy of particle. Then total energy of particle is rest mass energy plus kinetic energy. M naught c square plus K. What is E? According to Einstein's mass energy relation, E is mc square, right? Here, then K becomes m minus m naught c square. And this delta m is equal to, you take m minus m naught into c square. So kinetic energy is equal to delta m c square. What is this delta m? M is mass of the particle when it is in motion, and m naught is rest mass when the particle is at rest. It means mass of the particle in motion is always greater than the particle is at rest. That's why difference in these two masses appears as energy, and this kinetic energy delta m c square. This is Einstein's mass energy relation. You must remember this one, E equal to delta m c square. Okay, these are very small topics. It is very helpful when you solve the numericals also. After that, one small topic is there, mass defect. Please take a screenshot of this one first. Now, mass defect. You know, nucleus is made up of nucleons, that is protons and neutrons, and the sum of protons and neutrons together is always greater than the mass of the nucleus when it is at rest, when it is in a stable condition. That is called rest mass. Okay, so this difference in mass between the rest mass of nucleus and sum of masses of protons or neutrons is called mass defect. So you can define in this way the difference between sum of masses of the nucleons. Nucleons means protons plus neutrons constituting a nucleus, and rest mass of nucleus. Rest mass of nucleus means when the nucleus is at rest or a stable state. It is also, you can write nuclear mass, right? Rest mass of nucleus means nuclear mass is called mass defect. It is represented by delta m. So its formula becomes, suppose there is an element X, its proton or atomic number is Z and mass number is A, and number of neutrons becomes how much? A minus mass number minus atomic number A minus Z. Now total number of protons is how much? Z. Total number of neutrons is A minus Z. So ZMP plus A minus ZMN. This is the term inside the square bracket gives sum of masses of nucleons. Nucleons means protons plus neutrons, and this is always greater than the rest mass of nucleus. This Mn represents rest mass of nucleus, or you can write nuclear mass. when the nucleus is at rest or unstable state, and this nuclear mass is always less than the sum of masses of protons and nucleons constituting a nucleus, right? So this is mass defect, and this difference in mass always appears as energy. According to Einstein mass energy relation, energy can be converted into mass and mass can be converted into energy. So this difference in energy appears as energy, right? So this difference in mass can be utilized for energy purpose. So from here we can define binding energy. First, it will be more clear with the help of this example. What is mass defect? Suppose oxygen 816. 8 is what? Atomic number, and 16 is mass number, so number of protons becomes 16 minus 8, 8. So mass of 8 protons plus mass of 8 neutrons. 8 is common, mass of proton plus mass of neutron is given. It becomes 16.12744 AMU. By spectroscopy method, it is found that nuclear mass or rest mass of nucleus, when the nucleus is at stable state, its mass is 15.99493 mu. It is this nuclear mass is always less than the sum of masses of nucleons, means protons and neutrons. So this difference delta m is what? Sum of masses of protons and neutrons, 8 mp plus 8 mn minus nuclear mass, rest mass of nucleus mn, and this becomes, if you subtract this one, you get something, right now. So in this way you can calculate mass defect, and this mass defect appears as energy according to Einstein mass energy relation. So if you know how to calculate mass defect, you can easily calculate binding energy. Still binding energy is not in your syllabus, but you must know the formula. What is binding energy? Energy required to hold the atoms together inside the nucleus, because you know in the nucleus there is a strong electrostatic force of repulsion between protons. So some amount of energy is required to hold the atoms together in the nucleus, and that energy is called nuclear binding energy, and it will be equal to this mass defect delta. It will be appear as energy. If you multiply this mass defect with c square, you get, according to Einstein mass energy relation, binding energy, EB equal to delta m c square. So you can easily calculate binding energy also if you are able to calculate the mass defect, right? So this is about mass defect. After that, only one topic is left, that is nuclear reaction. Please take a screenshot of this one first. Now, the last topic of this chapter is nuclear reaction. What is nuclear reaction? It is the process by which identity of a nucleus is changed when it is bombarded by energetic particle. When a high energy particle is bombarded with any nucleus, that identity of the nucleus is changed. It means it is converted into different nucleus. Suppose this X is a parent nucleus, right? And it is bombarded with this high energy particle A. Now what happens after bombarding with this high energetic particle? This parent nucleus is changed into product nucleus Y plus another daughter nucleus B, and a large amount of energy is released Q. Why this energy is released when it is bombarding with a high energetic particle? Due to the difference in the masses of reactants and products. Here Q is nothing but, you know, delta M C square. What is delta M? A mass defect, difference in masses of reactants and products. Mass of reactant is always greater than mass of product. So here mass of reactant is what? X plus A. Mass of X plus mass of A minus mass of Y plus mass of A, right, into C square. This difference in mass appears as energy, right? And in this process, during nuclear reaction, a large amount of energy is released due to difference in the masses of reactants and products. It is of two types. This nuclear reaction, which is used to release energy, it is of two types. One is nuclear fusion and another one is nuclear fission. Okay. What is this nuclear fission? Fission means what? Breaking, splitting. It is the process of splitting of a heavy nucleus into two or more lighter nuclei, right? It is a process of breaking or splitting of a heavy nuclei into two lighter nuclei, and in this process a large amount of energy is released. The best example for this is uranium-235. First it is bombarded with this slow neutron 0 and 1. After bombarding with this uranium-92 with neutron 1, uranium-236 is formed, and then it is splitted into barium, krypton and 3 neutron plus large amount of energy is released. Barium is 56,141 plus krypton 3692 plus 3 neutron. If you want to balance this equation, you can balance this. Here mass number is what? 235 plus 1, 236. Here again 141 plus 92 plus 3 neutron, it means 3. It again becomes 236. Here atomic number is 92, right? And here also 56 plus 36, this becomes 92. In this way this reaction is balanced, and during this nuclear fission reaction large amount of energy is released. In this process 200 megavolt energy is released. Why this energy is released? Due to difference in masses of reactants and products. Mass of reactant is always greater than mass of products, and due to this difference in mass, that is mass defect, energy is released. Right? This is about nuclear fission. The best example of nuclear fission is nuclear reactor and atom bomb, which is not in your syllabus, so no need to discuss about these things. This nuclear reactor comes under, okay, I will discuss later on. Another type of nuclear reaction is nuclear fusion. Fusion means what? Fuse means combining together. It is process of combining two lighter nuclei to form one heavy nucleus. Here deuterium H12, 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 3 deuterium are combined. These are lighter nucleus. It combines to forms helium He24 plus 1 deuterium H11 plus 1 neutron, plus in this process also some amount of energy is released. That is here 21.6 mega electron volt. Energy released in nuclear fission is greater than energy released in nuclear fusion, but energy is released. Why? Due to difference in masses of reactants and products. Here mass of reactant during fusion is here also greater than mass of this product, right? This nuclear fusion takes place only at high temperature and pressure, that is in sun, because inside the sun temperature and pressure is very high. Inside the sun temperature is how much? 10 to the power 7 Kelvin. So inside the sun nuclear fusion takes place, and its example is hydrogen bomb. This energy is used to produce hydrogen bomb, right? So this is about nuclear fission, only this much topic is in your syllabus. Otherwise you can study about nuclear reactor, atom bomb, everything, but that is not in your syllabus for this year. Okay, so only this much is enough. Okay, one more thing, nuclear fission, this is of two types. One is controlled nuclear fission, another one is uncontrolled nuclear fission. Controlled nuclear fission means, you know, in one fission process 3 neutrons are released now, and 3 neutrons again bombarded with what? 3 more atoms, then again large amount of energy is released. So in this way uncontrolled nuclear fission reaction takes place. That reaction is uncontrolled, rapid, and the best example of uncontrolled reaction is what? Atom bomb. But by any means, out of these 3 neutrons, 2 neutrons are absorbed, so only 1 neutron is left. Then that 1 neutron again bombarded with uranium-235, and again 3 neutrons, a large amount of energy is released. Again then 2 neutrons are absorbed, and in this way only 1 neutron bombarded with the next uranium atom. So in this way nuclear fission reaction takes place in a controlled manner. So controlled nuclear fission reaction is controlled and steady. The best example is this one is nuclear reactor, which is not in your syllabus. What is nuclear reactor? You know, nuclear reactor, it is an arrangement to generate electricity. It is used to produce electricity, right? So no need to study about nuclear reactor in detail, just it's enough. Fission reaction is of two types, controlled and uncontrolled. So this is about nuclear reaction. Please take a screenshot of this one first. So with this, I am going to end the class. Hope you like this one shot series of class 12th physics. Please like, share, subscribe my channel. Okay students, keep revising and stay tuned with this channel. Thank you.